I have started the recording, so let's get started. Before we take up the subsequent topics or the slides on this topic, is there any question from anybody based on what we discussed yesterday? Okay, so if there is no question, I will continue. A quick recap. What we said is that we are going to see the use of these hash time locked contracts, and as we mentioned that when the contract is created, then it comes with a hash corresponding to a key value, and once this key is revealed, then that means that whoever can was supposed to claim this amount, like in this example, Alice created the contract for 1 Bitcoin, and it was the hash of this key, that is, say, I love strawberries, that was used. And then when can Bob claim this amount? Bob can claim only when the key is revealed. The other aspect of it is the timeout, that is, if either the key is not revealed or if key is revealed and for some reason it is not actually claimed, then after a timeout period, like in this example, it's 2 delta, the this amount would be refunded back to the owner. So in this case, for Alice. So this is something that is actually used for this atomic swap type of operation. Now, what it does is whatever is written here in this form, I will explain through a diagram in the next slide. Essentially, whatever we have said so far, this is what is listed here, that Alice would first actually create a secret, like that I love strawberries, which is shown here as that random, that x belonging to 0 1 lambda, and then computes the hash, and then it broadcasts the transaction that spends some amount Bitcoin into an output script. We know what these output scripts are from our earlier discussions, and then Alice can get back the position after a certain period of time. And as we mentioned, this time itself could be in terms of number of blocks. And Bob can redeem this number of Bitcoins by supplying the pre-image of Y. So whatever was that X that we mentioned. So once Bob gets X from Alice, then Bob can redeem these N1 Bitcoins. So what happens is that if now Bob is sending something back to Alice, so that is the whole point of swapping. So what Bob would do is that after this transaction that was created by Alice is confirmed by several transactions like C0 number of blocks, then it means that Bob is sure that Alice cannot go back on what she had created as the transaction. So first part, so what we had seen in the previous slide was only one part, that Alice is creating the contract, and then when Bob can redeem it, and if Bob does not redeem, then when Alice can get back. But our target is that Alice would give something to Bob and Bob would give something back to Alice. And typically, this could be occurring in different networks. So, after Alice created this transaction, which promises to pay Bob, and then that particular transaction was buried after a certain number of blocks. So, that means that Bob is now convinced that Alice cannot, as such, go back on that contract, and if Alice reveals the key at some point of time in the future, Bob will be able to get that money, that number of Bitcoins. So what Bob would do is that, say Bob is now willing to pay a certain number of ethers back to Alice. So what Bob would now do is that Bob would now create a transaction in Ethereum network. So the previous one, assume it was in the Bitcoin network, as was mentioned. So here it is Ethereum or LTC, the Litecoin network. So we are using BTC and LTC in this example. So let us stick to that example. So in LTC network, what Bob would do is that Bob would now create a transaction which says that it will pay into LTC to Alice, and what is important is that this also uses the same value for that hash, that is the y that was used by Alice to create her transaction. So the pre-image X is known only to Alice. Alice created its hash Y, which was used to create the transaction that was supposed to pay N1 BTC to Bob. And Bob, when he is creating this transaction of paying N2 LTC to Alice, Bob is also using the same hash, that is Y, but Bob still does not know the value of X. So that is what we have to keep in mind. So now Bob actually creates the transaction, and then Alice also knows after a certain number of blocks that it is buried. So, with high probability, now Bob cannot go back on his promises. So, now both the parties have committed, but still nobody can make the claim till Alice makes the this secret known. That is, that X is advertised. So after some time, when Alice is now revealing this X, then what happens is that Bob can now use that X and his private key to claim the N1 bitcoins that Alice had uh, kept in the transaction, and now also Alice can claim these N2 Litecoins that Bob had created in his transaction. So, so both the parties now can actually take back the money from the other side. That is, LTC now goes to Alice, and there's N2 LTC, and Bob gets this N1 BTC. So, what happens is that it all is dependent on that secret, that secret X that was created by Alice, and the rest of the transactions were actually created using its hash, but for redeeming it, the original value X was required. Now, this is a site that you can take a look at it, which gives a nice illustrative example, and that tells you a little bit more in details of exactly the same points that we just now mentioned, and it gives a nice analogy like creating some mailbox and how they can do it with respect to that particular way of ensuring that through this hash one can uh, actually lock these two in both ways, and then once the key is revealed, then both the parties can claim. Now you see that while this looks good, but there are a few things that can happen. That, say, uh, Alice put this in one bitcoins, but then Bob finds that no, this is not good enough for me. So Bob does not create his transaction. So then what happens? Alice has already committed it for Bob in her transaction. So, but Bob is not now creating. So what would happen is that after the timeout period, Alice would be able to get back those bitcoins. Okay. Or for example, that Alice puts her N1 BTC in the Bitcoin network, and Bob puts his N2 LTC in the Litecoin network. But then, for some reason, Alice is not happy. Say that N1 is to N2, that ratio is not satisfactory to Alice. So she expected some N2 plus some more amount, but Bob is willing to commit only N2. So what happens is that Alice does not really want to go ahead with this transaction. So Alice is backing out. So what Alice would simply do is that Alice would not reveal her key. So if Alice does not reveal her key, then Bob will not be able to claim, and what will happen is Bob's transaction will time out, and Bob will get back his N2 LTC, and after that Alice's transaction also it will time out, and then Alice will get back her N1 LTC. So that is how this both the hash lock and the time lock are together used in this hash time lock contracts. So we see this through this example, which is a nice pictorial representation. So Alice generates a secret key and computes the hash, and then Alice creates this transaction with HTLC of say 1 Bitcoin, uses the hash that was computed from the key, and then with some timeout period of say 4 delta starting from the initial time, say t0, and then this hash h is made known to Bob, And now Bob, once Bob sees that indeed Alice's this transaction is buried under a certain number of blocks, so Bob is now willing to verify Alice did create the funding HTLC with H. So once Alice shared that H with Bob, Bob can actually verify that Alice created the funding HTLC with H. And then when Bob is satisfied, now Bob will create this his transaction of 33 ethers, for example, with some more such timeout period. And then Alice also can verify that indeed Alice knows already H, so Alice can verify that Bob indeed created the funding HTLC with H. And then once Alice is satisfied with the fact that Bob's transaction is now buried under a certain number of blocks, so what happens is that Alice would reveal the key, and as Alice reveals the key, then Bob can, as by revealing the key, basically also means that Alice can now uh, claim these 33 ethers, which was created in this Bob's this HTLC with 33 ethers. So by because for redeeming that also the same key is required. So for redeeming both the transactions, the same key is required. So Alice knew about it, and Alice has anyway revealed it. And when after revealing it, Alice can claim back those 33 ethers which was created by Bob's transaction. But just as this key is revealed, so now Bob also knows the key, and then Bob can now redeem that Alice's HTLC 1 BTC. So Bob will get back his get that 1 Bitcoin. So in this fashion, what we have is that we have this atomic swap, and as I said before, that if one of them backs out, then after the timeout they will get back their amount, which is actually shown in the next slide. So we see that uh, Alice gets that 33 ethers and Bob gets the 1 Bitcoin. Now, in the second slide, what happens is that, as I had mentioned, if Alice does not reveal the key, so Alice does not reveal the key for the reason so that maybe Alice is not satisfied with Bob's 33 ethers. She might have expected 34 ethers or something like that. So these types of situations are also explained in the previous the link that I showed in the previous slide. So, see, if Alice does not reveal her key, then what will happen is that first Bob's transaction will time out, and Bob will get refund of his 33 ethers. And after that, when Alice's timeout occurs, then Alice would get back the 1 Bitcoin. Note that Alice's timeout is set after Bob, because otherwise, what could have happened was, say, Alice timed out first, and uh, say after Bob created the transaction, you see Bob HTLC 33 ether H sum 2 delta. Then after that, if say Alice times out, then what can happen is that Alice times out, then Alice would get back her own 1 Bitcoin, and Bob has already committed the transaction. Bob cannot back out from it, but then Alice knows this key. So what Alice could do was that Alice could first wait for her transaction to time out, get back her 1 Bitcoin, and then she would simply use the key to get back this Bob's money. So, and by that time, since it has timed out, so even if Bob knows about that key, Bob cannot do anything about it, because the money has already been refunded back to Alice. So it's important that we ensure that that Alice's timeout occurs after Bob's timeout. So if it occurs like that, so Alice cannot actually claim both her refund and also the payment from Bob, because as you see the way it is written here, that if Alice does not reveal the key, so Bob will first time out or get it, and then only Alice would get her refund. And why is it so? Why this asymmetry? It is because that Alice has more power here, because Alice had created the secret key, and so Alice knows the secret key, and Bob does not know the secret key. So Bob, as such, is at a disadvantage. So it's important that Bob's timeout occurs first, and then Alice's timeout occurs. Now, that was about two parties, and then we can extend that to a multi-party cross-chain swap. This is an interesting example, and it is taken from this paper, this atomic cross-chain swap. So this is a very nice example that here we have, say, selling of a physical asset. So Carol wants to sell her car, say a Cadillac, for bitcoins. Okay, Alice is willing to buy the car, but Alice is willing to pay in an altcoin cryptocurrency, not in Bitcoin. So we need another person who is also willing to trade these altcoins for bitcoins. Okay. So what we have now is a tripartite situation that Carol will pass on the title of her Cadillac to Alice, and so Alice would pass on her altcoins to Bob, and Bob would pass on these bitcoins back to Carol. So Alice, Bob, and Carol, they arrange a three-way swap. Alice will transfer her altcoins to Bob. Bob will transfer his bitcoins to Carol, and Carol will transfer the title of her Cadillac to Alice. So here, of course, what is important is that this is what I had briefly mentioned in the last lecture. That is that it is assumed that this title of the car. So this is also maintained in some form of a blockchain. So it is basically the transfer of the title can be done using a smart contract online. So it is not going to do something offline and then off chain and then try to take care of the payments in the chain. So this assume that this there is a network that actually keeps track of the titles and their transfers. So that is what is the assumption here. So it's a little verbose and taken from this paper, but it helps us to understand. So it's very similar that now Alice is starting this thing. So Alice creates a secret S and then publishes a contract on the altcoin blockchain with hashlock H and time lock 6 delta. So you need to note that this Alice is knowing the secret. So Alice's time lock will be the maximum. So it is some 6 delta in the future to transfer her altcoins to Bob. So it is very similar to the previous two-party example. So now Alice once has created that in the altcoin network, and Bob sees that it is indeed published there. So he publishes a contract on the Bitcoin blockchain and the same hash log, but H, but with the time lock. So it is a little less. So it is 5 delta to transfer his Bitcoins to Carol. Now, when Carol now sees that Bob's contract has been published, she would publish a contract on the automobile title blockchain. That is what I was talking about, with the same hashlock H, but now with timeout 4 delta in future to transfer her Cadillac's title to Alice. So now all the three parties know these things have been done. So Alice knows that if she reveals the key now, so you see that all of these three are using the same value of H, which are derived from the same secret S. So if this S is revealed, so everybody will be able to do the claiming. So when Alice confirms the Carol's contract has been published, she would send S to Carol's contract. So then uh, what happens is that she first acquires the title, and then because she has sent S to Carol's contract, so now S is revealed to Carol. So Carol then sends S to Bob's contract, acquiring the bitcoins, and then Bob now knows about this S. And Bob would now send S to Alice's contract, acquiring the altcoins, and this will complete the entire swap. So you see that it is a simple extension of what we had shown for two-party, but it works for three-party, and we can do it for multiple parties also. And of course, here we have this example that this how Alice actually has created that H, and then first it is hashlog of H plus 6 delta, and then the second one is created which is with 5 delta, and the third one is with 4 delta. And then we have first revealing of this S by Alice that would transfer the car, but that would also cause Carol to learn about S, and then she can now transfer the Bitcoin, and in the process would reveal S to Bob, and then Bob can transfer the altcoins from Alice's contract. Now, if we see this example, that what is so when it works, everybody sticks to the protocol, then it is all good. But then what happens if one of them backs out or halts? So if any party halts while contracts are being deployed, then what will happen? Then all the contracts eventually would time out and trigger the refund. So say Alice created this one, the first one, with H and then 6 delta, but then after that, Bob is not willing to proceed. So in that case, what would happen is that Alice would simply get back her altcoins after 6 delta. Likewise, if Bob creates his contract, but then Carol is not willing to proceed with that, then Carol would halt, and then after some time, Bob would first time out, and then Alice would time out, and they will get back this money. And likewise, even after Carol had created her contract, if Alice does not reveal, then after some time Carol will get refund, and then Bob will get refund, and then Alice would get the refund. So it will work nicely. Now, so, but when the so that was all if it happened before this key was revealed. Okay, but then while things are working, if any party halts during the triggering of contracts, only that party ends up worse off. This is interesting. So for example, uh, Alice had revealed the key, and then what would happen? Alice would get the Cadillac's title, but if Carol does not do anything, then she would not get her bitcoins. And then what would happen is that Bob finally will get a refund because of this timeout. So it is see that if Carol halts, then her misbehavior would only harm herself. The others will not be affected. And of course, the order in which contracts are deployed matters. So, uh, mm, so you see that if these are not done in this manner, then you can easily see that if she first posted her contract with Alice before Bob posts her contract with Carol, then Alice could take ownership of the Cadillac without paying Carol itself. And time lock values matter, as I said, that you have to ensure that as the keys are revealed and these are passed on to the other party, so they would be able to actually apply that key and then get back their money. So it is important that if something like this works, that if Carol's contracts and Bob were to expire at the same time as Bob's contract with Alice, then what happens is Carol could reveal S to collect Bob's bitcoins at the very last moment, and leaving Bob no time to collect his altcoins from Alice. So you have to ensure that these are that done these deltas are selected in such a way that there is enough time for people to collect. And in some cases these deltas, like it could be like in this example, if you see the one that I had mentioned, sorry, I am going back a little. So if you go to this site, you will see that they say that for some cases, like Alice's timeout could be maybe of the order of a week or so, and for maybe Bob it would be a matter of days and so on. So it can be accordingly set. Okay, so that there is time for people to actually do the collection of their money, and before that the previous party is a contract is timing out. So if they behave irrationally, if Alice reveals S before the first phase completes, then what would happen is that so Bob can take Alice's altcoins, and perhaps even Carol can take Bob's bitcoins, but Alice will not get her Cadillac. So you see that if it was at the stage when up to this was done, the second part, okay, that Carol has not created the contract, only Bob has created, and now Alice has revealed. So if Alice reveals, Bob will get Alice's money and Carol will get Bob's money, but Alice will not get anything. So again, if Alice misbehaves, only she is going to suffer. So it guarantees that if all parties conform to the protocol, then all the swaps would take place. But if some parties deviate from the protocol, then no conforming party would end up worse off. So as we have seen that the parties that they are conforming, they are not ending up worse off. And even if they try to collude, it will not have an incentive to deviate from the protocol. Just as any one party deviating or they collude to deviate, what happens is that by doing this uh, step of deviating from the protocol, they are not going to get benefits. So this is the interesting way in which such multi-party atomic cross-chain swaps can actually take place. Now there are a few limitations of this approach. So as you can see, that it is a bit slow and often takes maybe some hours to execute. As I said, that it all depends on who is publishing the contract when. So Alice could publish the contract first and then wait for Bob, and Bob could take his time to publish his contract. So there is nothing that the protocol itself forces Bob to do something within a certain time. And parties may not be able to respond to real-time price fluctuations, as we have seen that if Alice is paying in the two-party case, we saw that Alice decides to pay 1 Bitcoin, and she is expecting maybe 33 ethers based on the current rate, and then Bob is delaying it, and by that time maybe 1 Bitcoin has become 35 ethers. So Alice may not be satisfied with 33 ethers, and as I said, that Alice might not reveal the key at all. So these are the different possibilities, and some weak denial of service attacks could be there, where an adversarial party can repeatedly propose an attractive swap and then fails to complete the protocol. So they might agree to it, but then they finally do not live up to it, and they back out. So that would be causing triggering of the refunds. But you see that till refund occurs, as I said, that if it is a matter of weeks for getting the refund for Alice, then till that time you see her fund is anyway locked. So it could lead to this kind of denial of service. So Alice and Bob enter into a contract. Alice blocks her 1 Bitcoin in a contract, and then Bob would, on some pretext, will back out. So it is going to actually make Alice's that 1 Bitcoin locked for some time till the timeout occurs. So these situations can always occur, but otherwise you see that it is an interesting protocol, and then it can be actually used for doing these atomic cross-chain swaps. And if you remember that in one of our earlier slides, we mentioned that it is all about the atomic swapping that is required. And once, say, Bob gets this 1 Bitcoin in his network, so in his account, so then uh, Bob can, of course, make use of it at later point of time. So that was about uh, interoperability in the context of permissionless blockchains. And next, we will move on to discussions on permission blockchain. But is there any quick question at this stage from anybody? Okay, so if there is no question, then I will proceed further. So now we'll talk about permission blockchain interoperability. And if you remember in our last class, we mentioned that for permission blockchain, which are basically based on these cryptocurrencies and or of movement of assets, like we saw this title of cars and so on. So what happens is that there it was more important that these are taking place atomically, and also we need to worry about these exchange rates and so on, because this is about transferring of assets. In contrast, when we have permissioned blockchains, then it is more about transferring of data, and that should be a consensus view of the data that is to be transferred. Now, these permission blockchains, these networks, they are designed, as we know, are meant to be private for a closed consortium. And over the years, what has happened is that several different business sectors, uh, they tend to have different groups of organizations, and thus have separate blockchain networks. So the groups of organizations can have their own blockchain networks, and uh, as such, they are, as we mentioned, they are operating in isolated silos. But there is also a need that they would interoperate. So there are these different types of blockchain networks, like TradeLens, which is a logistics network, and so that talks about shipping and this transfer of goods so by road or by sea and so on. And then we have this trade finance network, which is called, one of that is we.trade. So there are of course others, and IBM Food Trust, so which is food supply chain, and we mentioned about some more during the first few lectures. So they keep operating in complete isolation from one another, but there is a need for interoperation between these isolated networks to achieve a common business goal, and that will benefit all the parties. So that is the context in which we are discussing this interoperation in permission blockchains. And this particular paper, the one that we are referring to, this was published in the 20th International Middleware Conference in 2019 in the industry track. And then it is also indeed a paper from IBM, so who are instrumental in developing this permission blockchain, specifically the Hyperledger project. So here the challenges for interoperation in permission blockchains. Here interoperation is specifically verifiable data transfer. So that is important. As I had mentioned briefly in our last lecture, that the data transfer that is being made from one network to another, so it should be verifiable, and they are otherwise separate permission blockchain networks. And also we have to remember that in these permission blockchains we also have these type of user management done, in the sense of authenticated users can do certain things and not everybody can do everything. And besides that, it is important that the the source network should be, if it is transferring some data to our destination network or the target network, the source network should be willing to actually share the data, and they should be sure that by sharing this data, none of their internal details or confidential information is getting shared with the other party. And similarly, the target network, when they are receiving the data, they should also be sure that this is not going to harm their own operation. So this is not going to have some kind of uh, uh, data that will mess up their existing networks data. So that is also important. So they should be in a position to actually accept the data from the other network, because they otherwise would not know what how much to trust. And there is no such notion of trusting a centralized party, which is quite obvious in the context of blockchains. So the data should be consistent with the source network's state, because that is going to get changed all the time. So it is important that whatever is getting transferred to the target network, that is consistent with the source network state. And then uh, the multi-party trust, in the sense that when one network consumes state from another, so that is what we are talking about, it would need to establish the validity of the state according to the shared consensus view of parties in the network. So they should get something that actually it is a valid state as per the shared consensus view of the parties in the source network. So this is what is important. So here we'll talk about one particular specific example, which is actually discussed also in the paper. So let me give you some introduction about how it works. Otherwise, you will not be able to appreciate. So first of all, if you see that there are two networks, and on the left hand side we have that we dot trade, and on the right hand side we have trade lens. So if you see here, we talked about this trade lens and we dot trade. And then what we is simplified is that it has got a lot of other features. Of course, this we dot trader is a full-fledged, it is a trade finance network, and trade lens is a full-fledged logistics network, which is actually used in practice by different companies. Now what it does is that it is just giving us a simplified view of that, with all the frills cut off, and so that we can focus on this transfer part only. So that's why it's called simplified vtrade, or SWT, and the other one is a simplified trade lens, which is STL. So just to show that they need have more features and functionality, which we are not referring to here. So we trade is a trade financing network. Means what? It means that if you look at this left hand side, this SWT network, okay. So there we have this notion of a buyer, we have a seller, and then there is a buyer's bank and there is a seller's bank. So for example, I'll take you through one example. So suppose there is company here which is going to import some raw materials from another country. Say there is a say yarn manufacturing company which makes use of wool from say Australia. So they would import wool from Australia. So here the buyer is this company here, and the seller is the company in Australia that would be selling the wool. Now, so how things work is that they would first negotiate uh, on some price, and then this buyer would raise a purchase order, which is the step one, as is shown here, on the seller. Okay, so they will say that, oh, we'll buy, say, 1 ton of wool at a price of, say, one a million Australian dollar. Just taking some examples. So now, so the that is what is contained in the purchase order, and which is happening off chain. Now the seller would, of course, will be selling the things. That means it will have to dispatch all this. But what is the basis on which it will sell? That it could happen that they will send their dispatch their 1 ton of wool, and then the buyer would say, no, I am not going to make the payment for whatever reason. Okay, so what happens is that in order to guard against that, so there would be this bank, and so there is a buyer's bank and there is the seller's bank. So buyer's bank provides what is called a letter of credit. So the buyer's bank, so this is a bank, say, in India, which knows the buyer, and they know that they have enough money to pay for those 1 million Australian dollar, and they would block that much money for from the buyer's account, and that is what is called a letter of credit. So this buyer's bank would propose that LC, and the seller's bank, the bank maybe in Australia, would be honoring this buyer's bank's letter of credit, meaning that if they say that, oh, this buyer has got this 1 million Australian dollars equivalent, maybe in Indian rupee, and if the items are received in order, then we guarantee that you will get this payment. Okay. So, but you see that this is something that is being done in this we trade blockchain network. Okay, so this is about the trade financing part. That is what we said, that this is about handling the money through the banks and all, and they can do it through these contracts that are created. So as we know that if something really gets done, then automatically the contracts would trigger, and then the rest of the things can work. Like when items have been received, if it is confirmed, then the contract would get executed, and the money transfer, etc., can take place between buyer's bank and seller's bank, and from seller's bank to the seller. So that is what this we traded is doing. But on the right hand side, we have this other one, that TradeLens, its simplified version, which is going to handle this supply chain, the logistics of transferring this shipping and all these carriers and all. That is being done by this other blockchain. So what happens is that now if you look at this blockchain on the right, so this seller will have to create a consignment, like they have to load all those wool in some containers and then book in some ship, the container ships and so on. So and once this ship is starting, they have what is called bill of lading. So BL, so bill of lading means that this consignment is actually being dispatched. So that is a confirmation that, say, a shipping company has received those containers and they have loaded it in their ship, and that is now being sent from say Australia and so on. So that type of stuff is being done. So that is what is handled by this other blockchain, which is this TradeLens blockchain. So the seller, when they get a confirmation that oh, indeed this LC has been approved by bank, so then they will request a booking through this second blockchain, the STL blockchain, and for sending it in a carrier, so which would accept the booking, and then actually the consignment. So this will be put in trucks and then sent to the port and so on. So all these things will be done by the second blockchain network, and then this carrier will be uploading what is called the bill of lading, that confirms that the items are now being sent. So that is the stuff that is handled by this STL, this trade logistics blockchain network. Now, what we are interested in is that now, once this is done, maybe once the items are being sent, then a part of the payment may be released from the seller, the buyer's bank, to the seller's bank. So that would mean that we have to have now this. You can look at this green dashed line, which shows that now between these two, we need to get this inter-blockchain data transfer to take place, which is that getting a copy of that bill of lading, which is a document that can let maybe a part of this payment to be made and so on.
So now all the others one, if you see that, if you look at this example, we have this seller which is part of both the networks. Okay, but then this bill of lading that has to move, that is a data transfer that has to take place from the STL blockchain to the SWT blockchain. So that is the context in which we are talking about this interoperability. So it enforces an obligation. So that is a bill of lading that we said on the buyer to make a payment. So that is the situation. So how this can take place, so that is what we are talking about. So what is important is that the verifiable data transfer, so whatever is there, it is a consensus view that indeed that carrier has received the consignment, it was created by the seller, and then it has been actually loaded in the container, and container is now going to this ship is now going to sail. So everything has been done, and there is a consensus view that indeed it has been done about all the details of the consignments, their quantity, and so on, that should add up to 1 tons, whatever. So this bill of lading now would be a consensus view of this second network, which now has to be transferred to the first network. So this is to happen through trusted data transfer. So each data in a network has a set of endorsements for consensus, because as we have understood that in both the sides there would be multi parties who would be actually approving it, like the seller's bank, buyer's bank on the left hand side, and they are the carrier's seller on the right hand side. And this set of endorsements would confirm the validity of a block in that particular network. Thus, from the source, data is accompanied with a set of signatures, which are also called attestations, that the seller has signed, the carrier has signed, and all of them have agreed that this consignment is now ready to move. And the attestations are validated in the destination network. Now it should be possible to validate in the destination network according to a data acceptance policy. Now this data acceptance policy would be specific to this network A. So network A is the destination network, and network B is the source network. So this is the overall architecture of it, that on the right hand side we have the source network, and on the left hand side we have the destination network. And each of these, actually in this particular work, this is referring to a hyperledger fabric network. And if you see that these two networks are exactly the same, they are, if you see, these are just the mirror image of each other. So this is an overall architecture of permission blockchain. So the special part about this is this membership manager, which is important for these permission blockchains, because they decide that who can do what, who will have what permission. So these are special about permission networks. And what we have is that we have these notions of, the more importantly, the data acceptance and the exposure control. So you see that it is there in both the networks, and we have now these two relays which are actually going to talk to each other, and then they set up this transfer of data with the consensus view from the source network, and then they should issue. I'm not sure if you can hear me. Yeah, so I think it is back. So what we are talking about is that we are talking about the situation that this configuration management contract maintains identity of the interoperating networks, the exposure control contract, which defines and enforces policies on what data to expose to which network. So this destination network, they will be getting it from the source network. So the source network would have to determine what is the exposure control contract. It means that how much of their data can be exposed to the other network. And data acceptance is validating the data that is received from a foreign network against the policy that defines how many signatures are required to verify a data. So it is important that the data that is sent from the source network, that is not going to cause any violation of their exposure control contract. And similarly, the data, when it is accepted in the destination network, destination network, it is also important that they really can figure out that this is data that is having sufficient verification done on the source side. So that is how this would work. And by this means, this bill of lading related data that would be coming from the source network, which is this, as we have seen before, that STL network, and it will reach the SWT network, which is on the left hand side. And once it is there, then it has to go in there into their own network as a transaction, and it will get verified and so on in through their consensus product. And we have the ledgers as usual in both the sides. So that is how actually it would work. So that is what is detailed here, that the steps are: proof request is generated consisting of a verification policy which has to be met by the source network. So you see on the source network that is being done, and the access control policies are checked whether indeed it is okay to send this data to the destination network. The response data along with proofs is sent back through the relay. So this is sent back through the relay, and proofs are validated against the verification policy in the destination network. So these are the broad steps. So initially the destination network will ask for that bill of lading. The source network would determine whether it can be sent, whether the destination network is indeed eligible for receiving this data, and then they will generate a proof request based on the verification policy, which should be acceptable to the source network. And of course, the access control policies would be checked at the source network, and then the response back against the request with the proofs will be sent through the relay, and this in the destination network would finally be validated. So that is what is shown here. The relays are doing this job. So if you look at it, that 1 2 3 4 etc. So basically the request is generated from the source network. I'm sorry, let me correct, it is generated from the destination network. The destination network is on your left. So that is the one which goes through the relay as a request, that you see the communication protocol between the two relays, and goes to the relay of the source network, which is 4. And there it is going to check these steps 5 6 7, which are shown here, that these are access control policies are checked, and the response data with proofs is sent back through the relay. So it goes back through this relay 4 as step 8 to the relay on the destination network, and then it goes back to the applications 9 and 10, and of course it would check through the configuration manager and the data acceptance stages. Those system contracts would check whether indeed the data can be accepted based on the policy, as is mentioned on this slide, that the sufficient number of signatures are there so that it can be verified in this destination network. So that is how actually it would work. So this is again is listed in this form of sequence diagram, exactly what I just now mentioned, that it is from the SWT chain code that it would go. So if you remember that it has to reach, as per our diagram here, that it has to reach on this SWT network from the STL network. So STL network is the source, SWT is the destination, and which is actually shown here, that the request originates from the SWT chain code. It goes to the seller client, SWT then a relay. It goes to the now this is the interblock transfer of the request going to the STL relay, which is on the right hand side, and the dotted line shows the boundary between the two networks. And then in the STL relay, it goes now to the STL chain code, and this access control validation is done, and then it checks the SWT configuration whether this is acceptable to send data, that exposure control is done, and then the result is encrypted, and then it is sent back to the relay, as you can see. Now the encrypted result with proof, now which is the SWT relay, which is now sent back to the SWT seller client, and if it is acceptable, then it will send an upload transaction with bill of lading and proof and other arguments, and then it will validate the proofs, and finally it will be executed in the transaction, and then the transaction would succeed or fail depending on whether all the different conditions are met. So that is the overall protocol, how it would work. So it is going to uh, make two of these networks interoperate, and there could be multiple such, but it would be extended using similar architecture. So that is about this interoperability. And the final one, as I had mentioned is yesterday, that will not take up now. That is about exchanges. So in our next lecture on Wednesday, we'll talk about security in blockchain. And once we have covered the topics on security, then we'll come back and talk about this tesseract and see how it actually takes care of certain types of security issues for these exchanges. So with that, we'll stop for today. But if there is any question, I would like to answer.
Sir, for the tutorial assignments, do all the assignments have same weightage?
So all the assignments do not necessarily have the same weightage because these are of different levels of difficulty, right?
Yes, sir. So if we miss a assignment,
Hmm.
then it's written in, like you said previously, that best 5 out of 6 will be considered, I think. It was something like that. So how will it be done?
Where is that written?
So I think in the starting of the course, best some assignments out
Was
of
it
all
about
will
the
be,
assignments or about the quiz?
sir, assignments, coding, programming assignments.
Okay, so we'll see that. So if of course if they are of different weightages, then definitely that if you miss one and taking best, we'll see how to make it work. But we'll check back what you are saying and let you know.
Okay, sir.
So for tomorrow, initially we'll have uh, the quiz as usual, and then we will have the tutorial.
Sir, hello, sir.
Yeah, yeah. Go ahead.
Sir, I have a question about the tutorial, current tutorial, current assignment. I'm getting a error in the in a in my program. Can I post it so that you can take a look at it?
No, no, no. What you do is that first of all, that the assignments that you are doing, that you need to do on your own. If there is something that you are not able to understand about the problem, you are always welcome
Okay,
to talk to the TAs. Okay, and they can
okay,
help
okay,
you.
sir. Okay,
Hmm? So get you in
okay, sir.
one-to-one touch with the TAs, and they will definitely help you out to the extent that it is about uh, about this. I mean, not that how to solve it, but rather about clarification. But to answer the
Okay,
previous
okay,
question
sir.
you asked, so I was just looking at the evaluation. So what we had mentioned that there will be three tests. Tests will take base two, totaling up to 50, and then five programming assignments, three long plus two short, 30 marks, and then six quizzes, and we'll take best five, which will comprise 15 marks and attendance five. So nowhere we mentioned that in the case of programming assignments, we'll take best something out of it. So I just now checked while talking. So it was about the quizzes. So quizzes will of course do best 5 out of 6. That is for sure. So with the assignments, we never committed about that. Does it answer the question who was asking? Shashank, did you ask? Who asked that question? Professor Chakraborty, you are also there, right? So that is what it is, right? So tests will be best 2 out of 3, and quiz will be best 5 out of 6. Okay, so I am stopping the recording, and then if